in this video, we will plot the step response for a spring mass damper system and determine the system characteristic values and compare the step response and the system characteristic values for different values of spring constant, whilst the mass and the damping coefficient remains the same. I will open up MATLAB, and in the working directory, I will create a new script and label it as task 6. After creating the file, I need to actually insert the values for the spring constant, damping coefficient, and mass. And this will follow the same architecture to what we did in task 5, because it's the same thing. Basically, the only difference is the system. So I will take 3 different k values, k1, k2, k3, 1 b value, and we need to assume the mass. That means m is 4 kilograms. So I will say k1 is equal to 12. So I wrote all the values for k1, k2, k3, b and m. Then similar to what we did in task 5, I will compute 3 different transfer functions for first system, second system and third systems, and I will call the first one num1 and enter the coefficient. So here the numerator coefficient is 1 over m. I don't need to substitute any values because I have already defined the variables. I will say this is den1 and den1. First coefficient in front of s squared. Coefficient in front of s squared is 1. So I will say 1. Put a space to separate. Coefficient in front of s is b over m. So I will say b over m. Space. Coefficient at the very end is k over m. So I will say k over m. So here I will have for k1, because this is only the first system, so I will say k1 over m, because b and m remains the same. Then I will compute the transfer function. I will say g1 equals transfer function of num1 comma den1. I will not put a semicolon at the end of this line, because then I can get the numerical interpretation of the transfer function in my command window. And I will obtain the step response. I will say step of G1, and I will run this. And this is the second order step response that I obtained for the given values. So like we did in task 5, you can right click, go to characteristics, and then click on peak response, rise time, settling time, steady state to get the values corresponding to these. So I will click those, settling time and steady state. And now we can see very well that the rise time is of 0.95 seconds. The peak amplitude is 0.0966. Percentage overshoot is 15.9 at a time of 2.11. And we can have the settling time, which is of 4 seconds, and then the final value, OKSS, at 0.0833. Now you can get a pretty good idea that there's a significant steady state error in this system, because the expected output is at 1, but the final value in this system is 0.0833. So this is how you can interpret it using the system characteristic values. Now I will actually replicate this for the other task, other 2 values of spring constant. So this will be num2, then 2, this will be k2, and I am plotting all the 3 system response in a single axis or a single window. So I will use hold on and hold off commands. Now I will run this. So then I will obtain three different step responses in single axis. So you can see here in three different colors. I can click this button to insert the legend. So that will tell me the different colors represent the different systems for G1, G2, G3. And I will right click, go to characteristics, go to peak response, and then I will go to rise time, and then I will go to settling time, and then I will go to steady state. So now you can see the effect of the of the spring constant, that is uh, you can see the effect of the spring constant in the step response. Now as the spring constant increases, which is our highest value is in G3 system, we can see the system performance is better, because instead of having a, rise time in the first system, we had a rise time of 0.95 seconds, but in the third system we only have a rise time of 0.4. The system has actually gotten faster. However, if you notice on the very right hand side, the final value has actually decreased, but our expected final value is at 1, but this has actually gone below our first system. So this is how you can click on these nodes, and this information regarding the settling time, rise time, and everything will be open, and you can basically do some analysis. You can maybe build a table and compare the values and do some explanations and etc. So this is how you can plot the step response for a second order system, as well as plot the step response of multiple iterations where you change any of the parameters. Like you can do this for the spring constant, you can do this for the damping coefficient or the mass, and see the impact of the system when you change these parameters. And lastly, I will actually save this uh, as a PNG file, because it will be, these things when you can include in your maybe your reports or any of your documentations in this as high resolution images, you can actually do a big interpretation, especially in the discussion section in a report. You can actually do a very high level interpretation using these graphs. I will say this is step 2.png. I will run this again. And not only the graphical representation, by not having a semicolon in the transfer function command, you can actually obtain the numerical representation of the transfer function. So this is the numerical representation of transfer function 1, this is transfer function 2, and transfer function 3, and you can see the values. The only value that is changed is the last constant of the denominator polynomial. And you can actually look at this in the PNG view as well. I will show it in the Explorer. And this is the interpretation, and it's a very clear image, and you can do a lot of interpretations using this. So this is actually the end of the 7 different videos that I put out for this introduction for MATLAB. especially relating to signal processing and control systems applications. But this is only a very basic level introductions for beginners, and you can use what you learned through these different 6 tasks and apply it into many different areas of signal processing and control systems. Thank you.